So thanks very much for the invitation. What a great crowd, and the whole summer school looks absolutely fantastic. There's certainly two of my PhD students here who I'm sure will be performing miracles for me after what they learn and experience here. And it's just a pity that I can't stay to hear some of the other speakers and to meet everybody, I'm afraid. But what I'd like to do is introduce you to an idea that actually has been around for quite some time. And this is the idea of probabilistic numerical computation. Now, what's this little chap? Smart ink is changing. Oh, right. No, that's far too advanced for me. And it fits really nicely into the summer school because it takes a combination of uncertainty quantification and a lot of the technical things that you've been learning about Gaussian processes and kind of puts them all together. And I guess a lot of the talks that you've heard so far, and certainly some of the talks you're going to hear next, have been pretty technical. This is a very not so technical talk, but what I'm going to try and do is give you ideas and try and get concepts across to you. So without further ado, the question is this idea of numerical computation as some sort of probabilistic construct, is it a new concept? Well, I've already told you that no, it's not. And after this presentation, if you're interested, there's a very nice website here, probnum.org, that has a reasonably good representation of the literature surrounding this particular theme. And it gathers literature from mathematics, computer science, and statistics. So it's fairly comprehensive. Now, I'm going to talk about a program of research that we've been pushing forward. And these are some of my collaborators who are working predominantly in this area. And the reason that I put them up is, well, because they're the people that are doing all the work. But more than that, it actually represents what I think is really exciting about this area and this theme of research. And that is that if I look at some of my PhD students and some of my former postdocs and collaborators, these are statisticians. So statisticians that work in theory, statisticians that work in computational statistical methodology, and Dino publishes an awful lot in probabilistic machine learning. And in addition to that, I'm working with some applied mathematicians. So these are hardcore card-carrying mathematicians, as Tim's talk will no doubt reinforce tomorrow. So I'm just the aperitif here, and Tim is going to be the large fillet steak that gets served, the hearty meal with lots of theorems and proofs and what have you. I'm just a sort of little light taster to get us going. And then, of course, there are also machine learners, so hardcore car-carrying machine learners like Philip and Mike. And what's really very exciting is that this nexus of applied mathematics, computational statistics, theoretical statistics, and machine learning, it creates a very, very exciting, a very, very interesting and very challenging area of research. And so if any of you are looking for an interesting PhD project or an interesting postdoctoral project, probabilistic numerics or probabilistic numerical computation is one area that is certainly an open field. There are lots of open questions and very interesting ones as well from all of these areas. So if you're more interested in computation and algorithmics, there's plenty to do. If you're more interested in the more fundamentals of the mathematical constructs, there's plenty to do, and so forth. Right. What is probabilistic numerical computation? Well, what I'm going to do, I promised you that everything was going to be fairly straightforward, and hopefully the first equation that I've put up doesn't pose any problems for you. So here we've got a little differential equation. It describes a function u, and the function u takes an argument t, which we'll just assume is time for this presentation. And the function u is implicitly defined. It's not actually written down, u equals something or other. U is implicitly defined by the function that satisfies this differential equation, that its derivative with respect to t is equal to some constant theta times the function itself. And furthermore, the other piece of information we're given is that the value of the function at t equals 0 equals 1. And so our goal is to find the function that satisfies u. So for those of you who are in machine learning, you could think of this as a latent variable problem. It's an infinite dimensional latent variable problem. We've got an infinite dimensional object u, a function. It's implicitly defined, it's latent. We're not actually told what it is, but we're given some hints about its form and its character by way of the left and right hand side of the differential equation, and in this case here, what the value of the function is at t equals 0, so the initial value. And our job is to then figure out what the latent function actually is and what its value is at any value of t. Now, of course, this is an absolutely trivial problem. It's one that we all learnt, we all know the function of way back in school. We know that the function that satisfies these two conditions would be the function u of t given this parameter, we'll call it theta, this constant theta, and it's just equal to the exponential of the product of theta and t. Now, of course, I could have put up something much more complex, and you would probably have to really rack your brains to try and remember all the tricks and the separation of variables and so forth, and what mathematical methods you could use to figure out what the solution was, and in some cases you couldn't. Now, the thing here is that despite us looking at this as a latent variable problem, a latent function problem, once we've got the solution, then this is a fully deterministic object. Right? So this little thing here, if this function describes our little world of growth or decay, then it's fully determined given the initial value. So once we know what the initial value is, then at any point in time in the future, we know absolutely what the value of u would be. Right? It's fully determined. Okay? So we've got a nice little clockwork model, representation of whatever it happens to be, our radioactive decay or our bacterial growth or population growth, whatever. Well, it's actually not quite as straightforward as that. And it's not straightforward because I just said to you that theta was a constant. Now, that constant might be something that, well, certainly God doesn't give to us in tablets of stone. It's probably some value, maybe a physical constant or a chemical, some sort of constant to do with chemistry or what have you. And it typically would be empirically derived. It's something that would be derived from experimental observation. Now, it turns out, of course, that as soon as we rely on measurements of some description, that immediately is going to introduce uncertainty into our little deterministic world. I might have some sort of measuring device which is really pretty poor. So Warwick University can't really afford terribly good measuring devices for measuring the value of theta. Whereas Neil, with the vast resources he has at Amazon now, where is he? He's hiding. Supplementing the vast resources that Sheffield have, he may have a super duper high precision measuring device to measure the value of theta. And the thing is that my value of theta, the uncertainty that I have in the value of theta, induced by the precision of my measuring device, and Neil's hyper-precise measurement, but nevertheless still imprecise, will differ. And for me, I will have most probably a higher level of uncertainty introduced than Neil would. Okay? So our uncertainty in theta, we can use standard schoolboy statistics to describe that uncertainty. And the thing is that that uncertainty in theta is not just going to, well, sit there on its own. It's actually going to propagate and introduce uncertainty into what originally was our little deterministic object U. And so if my cheap and cheerful measuring device actually has errors such that the precision is, say, 1 over sigma, and the errors are normally distributed, then, just by pushing this probability distribution through the exponential, it tells us that the distribution now, right, that characterizes our uncertainty in our function u, caused by our uncertainty in theta, is now going to be log normally distributed with a location and scale parameters which are defined here. So you can see that as time increases, our uncertainty is going to increase in the value of theta. So with any uncertainty at all, our deterministic object has become a probabilistic object. Okay, so that's the first message, is that you see a differential equation, you think this is completely deterministic, and absolutely, on A4 paper, it's completely deterministic. But as soon as you start using it to model the physical world, then, and you have to start making measurements, then that uncertainty in whatever, wherever it appears, is going to have an impact on these deterministic objects. Now, uncertainty can also enter in a more substantial way. It could well be that we had a differential equation which was far less trivial than the exponential growth or decay one that I described to you. It could be some highly nonlinear, coupled, multidimensional object where we just cannot obtain an analytic solution. We can't write down an equation that describes a function that satisfies our differential equation. So what happens then? Right? And in most, pretty much most applications of interest, so whether you work in medicine, you use pharmacokinetic and pharmacodynamic models, whether you work in engineering, whatever, if you're using PDEs or ODEs, typically you would not be able to obtain an analytic representation of the solution. So what do? Well, we resort to numerical methods to get approximations to the solution. Now, as soon as we use a numerical method to obtain an approximation to the solution, then we've added another layer of uncertainty into what the representation and what the value of this implicit function would be. So now we have, as Rumsfeld would have said, we have a known unknown. We know that there's something that we don't know. And again, if we just think of the simplest possible numerical method that we could use to solve this little differential equation, then we would use what we did at school and use something like Euler's method. And Euler's method would say that if I take my time horizon and I split it up into a little discrete grid where time starts at 0, and then at a time increment of h, I would have time 1, and then at another h, I would have time 2, which would be time at 1 plus h, and so forth. And I could then work out what the approximate value of my function would be at time n plus 1, and it would just simply be the sum of the value at time n, the approximate value of time at time n, plus the right-hand side of my little differential equation where I've plugged in the approximate value of the differential equation at time n, and I've scaled it by the time step. And the error that is induced by this numerical procedure is very well studied, and we know that this will converge as h tends to 0 to the actual solution. But we're not so much interested as h tends to 0, because if h tends to 0, we can't really do much. So for the little example that I've been working with here, if we plug in the right-hand side, then it turns out that at any of the discrete time points, the approximate solution is just going to be, well, this here, just 1 plus h theta raised to the power of n, where n is the discrete time point. Now then, so we've now got two sources of uncertainty. We've got uncertainty in theta, and well, we must have uncertainty introduced here because we know this is an approximation. Now, it's an approximation which induces an error, and in fact we can write down what the error actually is, but I'll come on to that in the next slide. So let's say we're a little bit better informed than we were in the previous example. In the previous example, I assumed that theta, the errors in theta were normally distributed. Well, let's now assume that theta, or we know that this process is describing some sort of growth, some sort of bacterial growth. So we know that theta always will be positive. And it turns out that our device, our measuring device, if we look at the user manual, tells us that the errors are going to be distributed log normally with a precision value sigma. So this uncertainty is now going to induce uncertainty which can be described by a probability distribution over the values of uppercase U. And the first two moments, so the mean and the second moment of that probability distribution is written here. So it's basically just a binomial weighted expansion of the higher order moments of the distribution for theta. But something else is interesting here. The numerical integration scheme that I've used is leaving an imprint on these moments and is therefore defining the probability distribution which characterizes our uncertainty in this object U. So not only have we got uncertainty here, but we've got uncertainty now induced by our numerical procedure. And so the deterministic numerical procedure, this little Euler's method here, is actually going to contribute further to our source of uncertainty. And we can characterize it formally as I've done so. So the numerical procedure, I am arguing, should now be viewed as an inference procedure, a statistical inference procedure. In other words, it defines a probability measure from which approximate solutions to the differential equation can be drawn. Now, let's take a step back. Let's assume that we're like most tame mathematicians. We assume there is absolutely no uncertainty in the initial condition, and there's no uncertainty at all in our knowledge about the value of theta. So the only thing we don't know is the function, the implicitly defined function itself. So everything now is fully deterministic. There is no uncertainty induced in our function u because of uncertainty in theta. And so, taking Euler's method, we can actually write down an expression for the evolution of the error as time progresses. So the error that we make is fully deterministic, right? So the error that we make at discrete time point n plus 1 is just going to be the error at the previous time step plus some residual term, and then the mismatch between the numerical approximation at time n and the true value scaled by h. So there's absolutely nothing random about this. This error develops and evolves completely deterministically. Right? Nothing stochastic about it. But there is a small problem. There's a small issue here. And the small issue is that despite this, despite we can write this down, and despite we know that this is fully determined, the evolution of the error is fully determined, we don't know what it is. You can't compute it. And so we have to resort to a branch of probability, of probabilistic inference, known as subjectivist probability. So we take a subjective view, and I hinted at that earlier on where I described Neil's Amazon-type high precision measuring device and my really crappy little measuring device, indicating that our uncertainties were personal and therefore the probabilities that would be induced by our information was subjective. And so there's a long tradition, a long history of subjective probability within the Bayesian tradition, going right back to De Finetti and onward to more modern day statisticians. And so I'm going to argue from a subjective probability perspective that numerical procedures should in fact be viewed as inference procedures. And I think this description here, this example here, I think really shows quite clearly that despite mathematically showing this is completely deterministic, the point is that we don't know what it is. We can't see anything about it.
So the reason we don't know it is because we don't know un.
We don't know that.
And r is r?
Yeah, well, r is going to be a function of u as well, because it's the higher order components of the Taylor series. So, as far as little differential equations are concerned, what the probabilistic numerical computation community have been arguing for is that rather than viewing a solution to a numerical computation as a numerical procedure, is that we define it as a procedure which produces a probability measure which captures in a coherent way all sources of uncertainty. So it accounts for them and presents those sources of uncertainty as a probability measure. Okay, so du by dt equals theta u is maybe not really stretching the boat out. So, so here's Navier-Stokes equations. Nonlinear, time-evolving, partial differential equations defined on a torus, 2D torus. And what I'm showing you here are 6 realizations of a solution drawn from a posterior probability measure describing the Navier-Stokes equations. And this is disturbing. Okay, so had Amazon given us all the hardware, I'm sure that we would see the video moving quite nicely. Yeah, so this isn't going to work. Okay, so what you would see is the time evolution from this initial condition of the vorticity of the fluid, and what you would see is the variability in those, and that variability is because of our uncertainty in the viscosity of the fluid and in the fact that we're using a discrete mesh over the torus and a discrete mesh as this surface marches through time. So this isn't a radically new idea by any manner of means. So statisticians like Percy Diaconis, Joseph Cadane, Tony O'Hagan from Sheffield had been developing these ideas and this philosophical view from way back. But what's really interesting is that if you read the mathematics literature, way back in the 60s, early 70s, mathematicians were saying, okay, we want to approximate a function. Let's put a probability measure over the space of functions. And okay, they didn't do any statistical analysis, but they were concerned about, you know, what is the average error that would be induced here. And if you look at an awful lot of that analysis, you can see how they were almost close to developing probabilistic numerical methods. And of course, John Skilling, a physicist who developed an awful lot of the early max entropy methods and was one of the early proponents of Bayesian methodology in the 80s and 90s, have been here long before I arrived in the scene. And so what I am arguing for is that this probabilistic numerics method, it provides a model of numerical uncertainty. And that model of numerical uncertainty can then be propagated through subsequent computations. And one of the important things, what's really exciting about being a statistician or being someone that's working in machine learning or data science or applied mathematics, is that a lot of the mathematical models, a lot of the statistical models, computational models that we are developing and studying are actually being used in commercial enterprises. They're actually being used by engineers to study and to help design, you know, complex processes and complex structures. They're being used by biological and medical researchers to study and you know, to help try and find therapies for, you know, certain types of diseases and so forth. They're also being used, God help us, by politicians in helping to form policy. And so it's incumbent on us to ensure that wherever there is any uncertainty, then we should account for it and ensure that it's embedded within our model structures and that it's propagated through the whole inference and through the whole reasoning and computation process until it gets to whatever government minister's office. So it produces probability measures over all unknowns. The residuals will have structure in them, which again can be propagated for or through to subsequent computation, and I'll give an example of that later on. And I mean, the other thing is that for the sorts of models that we're dealing with, so we have collaborators in the US, and they're modeling the flow of the ice sheet and the polar caps. So these are non-trivial models. Right? These are running on tens of thousands of machines just to solve the physics of the model. But in addition to that, they're getting major sources of data from NASA, images from NASA, which they're then assimilating into these models, and time course data and so forth. And there is definitely computational sticking points, shall we say, when it comes to problems of that size. And being able to identify where they are, again, from a probabilistic perspective, is turning out to be extremely important. And I suppose at the end of the day, it really safeguards against any unwarranted optimism in decision making or policy formation. So let me give you a little working example now that's perhaps a bit more interesting than the little example I just gave you. So differential equations, data-driven engineering, describing what happens when we do fracking, for example, underground. What happens if pollutants are released, and how are they going to actually travel, again underground, or if this is some sort of oil field, which in actual fact this is. This is a model of the Teal South oil field. So we would use these sort of differential equations in data-driven engineering. I mentioned in medicine, in clinical medicine. And what else? So another area which is really only just starting to emerge, but it's very exciting, is this whole area of computational social science, where now we can get a lot of data about the movement and infer the intent of people within whole populations. And here is an example, a working example that my group is working on with the Metropolitan Police, which is the occurrence of certain types of crime in certain boroughs of the city at certain points in time throughout the day, throughout the week, months and year. And what they're interested in, of course, is where can we best allocate police resources at certain points and at certain times of the day and of the year. Okay, so all of these are using differential equations, and all of them have relatively large sources of uncertainty. Right, let's work through a little example just to fix the ideas. So here's a very standard elliptic partial differential equation. It's the heat equation, if you want to think about it. It's just a standard diffusion. So we have the divergence operator, we have kappa, which is going to be our unknown. It's the diffusion constant. It's a value which could take distributed values across the physical domain, or it could just be one constant. And then we've got the gradient of the function u. So this could be temperature if it was the heat equation. It could be pressure if we were looking at fluid flow. So what we're saying is that the left-hand side is equal to this right-hand side, and this function here is a forcing function. And on the boundary, so if we just think of this here, so D would be the interior of our domain, and delta D would be the boundary. Okay. So on the boundary, then the unknown function takes on a particular value, b of x, and again that could either be constant or it could be distributed depending on whereabouts you are in the boundary. Now, we can't get access to u of x analytically in general, and so typically what is done is that a partial differential equation solver would look for an approximation which is a finite dimensional representation of our function u. So we're looking for a subspace of the infinite dimensional space that u resides in. So we're looking at this n-dimensional space. It's in a very familiar format. It's just going to be a weighted combination of basis functions. So a very familiar construction for you. Now what we want to do is quantify the error in u hat and do that probabilistically. So the inverse problem, the Bayesian posterior problem, would ask, okay, I don't know what kappa is. I want to know what the posterior distribution of kappa is given some measurements, noisy measurements of u. And there are lots of examples of this. Electrical impedance tomography is one example, practical example where this equation actually holds reasonably well. And so I'm sure you're all familiar with this, but the Bayesian inverse problem would say, well, we've got kappa, we're going to put some prior distribution, or prior, on kappa. We're going to gather some data, yi, and then given that data, we're going to turn the crank, given the likelihood and the prior, and induce a posterior over kappa given y. Now, the thing is here that, remember, we're uncertain about u. So we need to account for the fact that we don't have the actual value of u in our computation here. We've actually got an inaccurate representation of u. So we want to account for that in our Bayesian problem here. And just to show you that it is important, if we completely ignore the fact that we are using an approximation for the function u, and we run our standard Bayesian inference over kappa, then for a very simple example where the true value, data generating value of kappa was 1, then as the approximation gets more accurate, so as the number of elements in space becomes greater, and therefore the sort of discretization level becomes finer, then what we see is that the posterior moves from some biased representation and starts to concentrate on the true value. And we would expect that. The mathematical analysis of the finite element method tells us that it's a consistent scheme. So we would expect that to be reflected in any induced posterior. But what's rather troubling is that for a coarse mesh, then our posteriors look something like this. So they're biased, fair enough, but the issue here is that the level of confidence is such that it doesn't really indicate that there may well be a bias problem. And in fact, the bias is, and the level of certainty is so high that the high density regions of this posterior don't even touch what the generating value was. So this is really quite concerning, and this is one of the dangers of not accounting for all the sources of uncertainty, and even the uncertainty induced by what we might consider as a black box numerical procedure. On the other hand, if we do honestly account for the numerical uncertainty, then we induce a Bayesian posterior which looks, a series of posteriors which looks something like this. And this is far more reasonable from a statistical perspective, where now the uncertainty induced by a very coarse mesh is reflected by huge amount of uncertainty and inflation of the variance in our posterior. So this all makes sense, and hopefully this is a good pictorial representation of the scenario that we're working with. So let's go back to the forward problem, solving for u and doing it probabilistically. So I'm going to write the elliptic operator in shorthand, and I'm just going to say the A, represents that, nabla dot, nabla k u, right? So this is just the elliptic operator. So it's just shorthand. So our forward inference procedure would look something like this. What's our unknown? Well, this is our unknown. So we could reasonably place a prior measure on the function u, on the space of the function u, and we'll represent that by pi of u. Now, there's a whole literature, and there's a whole literature waiting to be written about how we're going to define these priors. And I think that there's a really exciting area for Bayesian statisticians, for machine learning people, and for applied mathematicians to take ideas from all of these areas and trying to, in some subjective way, define what would be an appropriate prior for a certain class of function given a certain type of PDE. So this is not a straightforward thing to do, but at a conceptual level, it's something that we can do. Okay, so we've now placed some sort of prior over our unknown function. We can then gather data. We can gather data by just probing the value of our forcing at particular points in the domain, and that gives us our data. And again, we can just use the Bayesian machinery to obtain the posterior of our unknown function given the values of the forcing that we've been able to obtain. And that gives us our posterior. Now, as this is a Gaussian process, summer school, it would be remiss of me to use anything other than a Gaussian process for the prior measure over u. But it actually turns out that there are some very reasonable and very beautiful reasons from the applied mathematics literature as to why a Gaussian measure is actually very reasonable. And in some cases, probably one of the few choices that we would have of placing a prior measure over unknown functions. But I won't go into those, and you can look at some of these papers, especially this one here or this one here. Although I would think about every 2 pages you read of this, you'll need to lie down for a nap. It's quite, yeah. You'd agree, Tim?
Possibly with an aspirin as well.
Right, with an aspirin as well. Okay, so let's turn the crank. So you've seen all this. It turns out that using a Gaussian process prior, or a Gaussian measure, as the prior for u, that the posterior, once we've probed the forcing value, right, so the posterior for u, given values of the forcing, is also going to be a Gaussian process in this case. Why? Well, because this is just a linear elliptic operator, and so we have closure of Gaussian measures under linear operators. And it turns out that the mean will look something like this. So A is our elliptic operator, and A bar is going to be the adjoint of the operator. K, you've guessed it, K is going to be the covariance function computed at all of the points in the domain where we obtain the value of the forcing function G. And this all looks familiar to you. But what's really nice is that for numerical analysts this mean function is in actual fact the approximation that a symmetric collocation method would return. So what we are obtaining in the mean is what a numerical method would return, but we've now got this very important measure of uncertainty in the solution. This is really important. It turns out that for this prior, for a Gaussian process prior, then the contraction of the posterior mass over the functions will concentrate on a delta function around the true value of our unknown function, and it will converge at a rate which is governed by a number of parameters, which are not surprising. So it's going to be determined by the fill distance. So how densely or how effectively have we probed and meshed the actual domain. So clearly as h gets smaller, as the fill distance gets smaller, then the rate's going to increase. But because we're taking a Bayesian point of view, the influence of the prior is going to be here, and we can see that the smoothness of the prior is going to regulate the rate of contraction of the posterior, as does the order of the PDE, in this case it's second order, and also the dimension of the domain, as you would expect. So this is all good. So we know that this thing is consistent. We know that it's going to converge at certain rates. This is fine. Let's just look at a quick example. It's probably one I should have given you for your Python type working sessions. So we've now said that kappa is equal to 1. It doesn't vary with x, and we're just working in one dimension, x. Okay, and the boundary values at 0 and 1, u is just equal to 0. So we're going to again place a Gaussian process prior on our unknown u, and the operator now is just going to be the second derivative, and the adjoint is the second derivative with respect to the other ordinate. And by golly, even this isn't working. So this is a nice animation, and it's not working. Anyway, for a forcing which is sinusoidal, then the actual function, the solution of this little PDE, is defined by the dashed line under there, and the posterior mean is the solid line on it, so that we're doing well as far as the posterior mean is concerned. But the main addition is that we now have our high density regions. We now have our levels of confidence in what the function values would actually be because of the discretization level that we've used. So this is quite nice. Now, this is great. We've got a probabilistic solution to our PDE. We've got a probability measure which captures our uncertainty due to the fact that we're using a numerical scheme, or we're not so much using a numerical scheme as we are approximating the infinite dimensional function which satisfies the PDE by a finite dimensional representation in some basis. So we've captured our uncertainty, we've accounted for it, and we now have a calculus which describes it. Well, the next thing we want to do is we want to propagate this uncertainty. And the way that we can do that is by looking at the inverse problem. Just a couple of other things. The sort of traditional measure of the error that a numerical analyst would use, again, if you had the oracle of the actual true value against the numerical solution, would look something like this. But because we have a probabilistic representation, our error would be something like, well, what would we use? We would use the trace of the covariance function, posterior covariance. And you can see it's of the same order and decays, in a sensible way. So we have a diagnostic as well in the posterior covariance structure. So this is nice. Right, we want to propagate. Neil Lawrence commented on your post. That's Facebook telling me Neil's clearly tuned out and is playing with Facebook at the moment. There's no hiding. No, I believe I started at 10 past, or was it quarter past? Where's the red brigade? 10 past. So I've got 10 minutes left. So this is just enough time to cover this. Yeah. I'm going to dismiss it. Right, so the inverse problem. So the inverse problem, I mentioned to you, we make some measurements with data, and what we're interested in is this diffusion constant, or this diffusion tensor, whatever. We want to do inference on this. And we're going to have data y, which is some representation of u, and so we want to just be Bayesians and just do the usual thing. But now, because you've heard this talk by Mark, and you know that, oh, I can't afford not to at least be aware of the error induced by the fact that I'm using some numerical procedure to estimate u as well. So, again, this is a very simple example, and I'm really just putting this down for, well, really just so that we can get the ideas across, and I'm not cluttering up the presentation with, you know, MCMC that has to be used, or, you know, approximate methods that have to be used. This is all nice and simple. So what we're going to say is that our data is actually a measurement of the true underlying function, so the true temperature, and it's contaminated with some noise, which is Gaussian. And so that would imply that the likelihood for our data y, conditional on our unknown kappa and the function u, would just be normally distributed with a mean of u, where u is the actual solution of the PDE, and then the covariance of the noise. Now, of course, we don't know u. So we can't close our eyes and just say, well, we'll just replace u by u hat and hope for the best. Well, if you do, then you see the sort of biased inferences that you could, and overconfident inferences you potentially could make. But remember that when we solve our PDE probabilistically, we have our posterior probability measure over the function u given our probing of the domain. And so what we can do is we can marginalize the value of our unknown function u by taking the likelihood and then weighting it with the posterior and integrating with respect to the posterior measure of u. And so we get a likelihood, which now, in this case here, because everything is normal, is also going to be normal. It's going to have a mean, which would be the mean of our probabilistic solution to the PDE. And then the covariance structure is going to be a combination of the measurement error for our data and our uncertainty in the unknown function u. And again, a little bit of theory tells us that the posterior for kappa, given our data, if we use this likelihood here, will contract to a Dirac, provided that the fill distance or the mesh size, right, in our numerical procedure is satisfied or satisfies this condition here. So h is going to be of order 1 over n to the, so again, beta is the smoothness of the prior, rho is the order of the PDE, and d is going to be the dimensionality of the space, and n are the number of data points y. So this also gives us some indication as to, you know, if we do want consistent contraction, then we should be meshing up at this rate. So if we go back to our toy example in the last 5 minutes, we want kappa. We know that the process satisfies this PDE and this boundary condition. And what we've done is we've just generated data from this where kappa, the true value of kappa is 1. And we've made measurements at these 2 points here. And the measurements have been corrupted with Gaussian noise. And what we obtain if we ignore the fact that we don't actually have access to the function u, and forget about the fact that it's introducing uncertainty, then we see the bias that I described previously. We see the bias, and we see the fact of this overconfidence until until h really starts to get to the sort of level that that we should be operating at. On the other hand, if we take a probabilistic perspective and account for our uncertainty, explicitly account for our uncertainty, you can see that the variance in the posterior gives us the coverage that one would hope for. So this is a very compelling example, but a very straightforward one. And in the last 3 minutes, let me give you a very compelling, far from straightforward example. This is a nonlinear PDE, which means that all the nice Gaussian process closed form solutions that I showed you will not follow. We have to use MCMC, but we're also looking at variational approximations as well. And furthermore, because this is a nonlinear PDE, it doesn't have just one solution. In this particular example, we know that there are 3 solutions. So the fact that there are 3 solutions means even more uncertainty, and we're going to account for that. So again, I won't give you all the technical details about how we take a PN approach to the inverse problem of inferring theta. One of the nice things is, I mentioned to you that because we have a posterior, and we have a posterior covariance, the posterior covariance turns out to be one of the main elements for Bayesian experiment design. And so we can use Bayesian experiment design to actually identify whereabouts in the domain we should actually be putting our mesh points or making our measurements of the forcing function. And this is an example where we just arbitrarily threw down some points and then used optimal design procedures based on the covariance structure of our posterior over the unknown function, and we reap those benefits. Again, if we ignore the uncertainty induced by the finite dimensional representation of the function, we can see some dreadful bias, and we can see some dreadful overconfidence until we really start moving down to quite a fine mesh. Here, we still get the bias, but we get a far more honest representation of our levels of certainty, or uncertainty in this case, in the inverse problem. Okay, I'm not going to talk about parabolic systems. I'm not going to talk about modelling crime within the London boroughs. My house is round about there, which is right next to a hotspot, rather alarmingly. I'm not going to talk about integration or Bayesian quadrature, though there's tons of really cool stuff there. I'm going to go straight to the conclusions. So, probabilistic numerical computation. It's most certainly not a new concept for numerical computation. But I think the time is right to really start taking this very seriously. It's a way to formally account for and quantify uncertainty in the whole pipeline of computation. And contemporary science, engineering are more and more reliant on very sophisticated mathematical representations of whatever. and numerical computation is being used more and more, and the complexity of these objects is becoming higher and higher, that what is feasible, or what used to be feasible, is now really starting to creak at the seams. And so accounting for and quantifying our uncertainty is becoming quite of fundamental importance in supporting coherent reasoning and subsequent decision making under these levels of uncertainty. I would just finally say that I think this is a really awesome area of research. It is at the intersection of mathematics, statistics, computing science, machine learning, data science, and you should come and join us. Finally, I always have to say thank you to those at Polaris House. Neil, fortunately, doesn't have to do that. And these are, so Lewis and Carla are here, and they're going to be GP superstars when they get back to Warwick. And you've all seen this thing on Facebook, where we've all submitted the paper and we're all looking really smug. And then about 18 months later, the paper's accepted, and it's had quite a toll on me for sure. So thanks very much, and I'm sorry I can't stay much longer.
So I realised I didn't introduce Mark. He's a professor in the Department of Statistics at Warwick, and does some great work bridging those different areas. So questions?
Especially from those of you that really think this is nonsense. I'm ready for you.
These are impressionable.
Yes.
I don't think this is nonsense.
God bless you, young man.
Same problem, but in plasma physics. So, what are your thoughts on, for example, you were talking about NCNC inference for nonlinear PDEs in the case of nonlinear systems. What are your thoughts on actually exploring the theory of higher order processes? So far with Gaussian, we actually talk about
Two moments.
Up to second moments. Do any members of your team see any potential for development of higher order processes?
I mean, I think that's something we've looked at. I mean, Tim, you might want to maybe comment on
So the nonlinearity.
nonlinear.
Yeah, the nonlinearities we've considered so far, we've been able to crowbar into Gaussian framework. So for consideration, differential operator is linear. If you can decompose it as linear plus something monotone and invertible, you can pull almost the same tricks. We haven't gone beyond that regime yet. If we do, then I think higher order processes might be the kind of tool we would need. But at the moment, we haven't seen the need for it.
I mean, also the fact that we're in essence using measures on function spaces, and there are not that many measures that have translation and variance and so forth in these spaces, and Gaussian measure happens to be or certainly one of them anyway. Well, yes, of course, the Laplace.
It's not invariant, but we know how to how to change it when we do so.
This is one of the great things about working with the mathematician. Keep you
honest.
Keep you precise.
So one of the characteristics of Mark's talks is he always has a bit where he says this is schoolboy math. And normally it never is, but today it actually was.
It was, yes.
It was, today it genuinely was. It was the first order differential equation. It was schoolboy math in 1990, I don't know.
Yeah. But yes, plasma physics. So we're working with a number of people that work, well, actually in quantum chromodynamics, who are interested in this. But the issue that Tim and I were talking about is that you're then working with conservative systems, and actually there's a whole load of technical issues associated with that.
I think I'm trying to make a bridge between what you said now and what Jeremy was saying yesterday. So he was talking about this probability distribution to quantify this discrepancy between
yes.
The reality.
Yes, that's a great. Okay, so what I've done here is I have assumed that that equation is the model of reality. Okay, so there's another layer of uncertainty in that it's absolutely clear that for quite a number of things in very complex systems where there are multiple levels of physics, for example, that the mathematical model will not be the actual reality. And so how do we actually model this? And so Tony O'Hagan and Mark Kennedy had quite a groundbreaking paper in the early 90s, or maybe early 2000s, early noughties, where they were looking at computer emulation. And no doubt this is what Jeremy was talking about, where you would actually add some component. Now, it turns out that, the thinking now is that rather than having an external component trying to describe the mismatch between the mathematical representation and reality, is to actually have an intrusive one. To actually say there are components in here which we're not entirely clear about. We know that they don't represent reality, and so we're going to capture that within the actual model itself. So this is a whole new area, a very exciting one, because now applied mathematicians are really starting to look at this and are looking to card-carrying Bayesian statisticians to keep them right. So it's very, very exciting.
I guess the problem that I always find with these is, especially when I work with biological life scientists, so you can always keep on building a level and a hierarchical Bayesian model.
Yes.
You can always keep on going up in level.
Yes.
But at the end of the day, you need to stop somewhere, and because they're going to get confused if you keep on putting.
So with biology is an interesting one because the level of uncertainty. So if you sit down with a biologist, cell biologist, and say, right, I'm going to convert what you understand about whatever process it is let's convert it into a formal mathematical model. You lose sleep very quickly when you realize that there are many ifs and buts and maybes and, well, this could be that. And so one wonders if, a purely mathematical representation is sensible and perhaps a more data-driven representation where these levels of uncertainty are much higher. But for physics-based models, where there is a good understanding of the underlying physics, then leveraging these mathematical representations within the overall statistical representation, I think is sensible. But modeling the mismatch between reality and model is quite interesting. But that's something that, that's another layer of uncertainty. All I'm doing here is saying, look, if you guys are certain, if God has told you this is the truth, then he hasn't actually told you what the answer is, so you're trying to figure it out, then you better make sure that you account for the fact that you don't know what it is.
For a full analysis, I like what you say, for a full analysis you kind of want to do both. You want to have the internal terms and an overlaying sort of description on top.
Yeah.
But I will talk a little bit more about this tomorrow. It depends how much you care about your model, right? And it depends what game you're playing. Are you playing the game of, I want to present the simplest model and see what I can get away with and mimic my data that I've seen? Or do I know there is stuff which is missing? Do I know there are uncertainties that I have not accounted for? And these will be important about making predictions or designing new experiments. In which case then all the uncertainties we're talking about here and others become important.
So this is the known unknown and the unknown unknowns
Bingo,
talk.
right.
Yeah, no one knew when Rumsfeld said that, just how
Yeah,
it
yeah.
was going to be.
I don't know how many citations he's got.
Statisticians were like, wow.
Wow, he gets it.
We all became Republicans. It's amazing.
But it was, I think the interesting thing about that is it's a spectrum. I mean, I like to think of it as a spectrum. So Mark characterized it as physics versus biology, but actually with the increase in data availability and the increasing importance of modeling, because the data is not coming through in a well-designed experimental way, you just find yourself sitting somewhere between these two extremes, purely data-driven and model-based. But I think that is, for me, one of the major motivations for probabilistic numerics. Because now it all gets confusing, and you want a consistent language across those games. And there's this trade-off between your computational demand. So in theory, you can compute forever and solve these Euler equations for whatever. But actually, maybe there's some data coming in on one side. So you've got to make these trade-offs between how much computation you want to make, perhaps how much experimentation you want to make, and pull it all together. And to me, the only language that allows you to do that is probability. So you want the numerics to have that probability in it.
Yeah. So this is an example where there's no physics at all. So this actually, these are reaction diffusion equations which describe how criminal activity diffuses within a particular domain over time, and how certain hotspots of criminal activity will develop. And actually, these emerge from an agent-based model. So these are the continuum limits, the mean field continuum limits of an agent-based model. So there's no physics in here as such. So it's what you say, just how much you believe in your model and how much do you trust it. So you don't really want to trust these terribly much.
But I think that's really because Mark had the title earlier, computational social science, and these methods are bringing in some computational methods into social science. But this is actually the second wave of that happening, because people tried this in the 19th century, and then mathematical statistics emerged as the way of dealing with that. But now going back to introducing these models, having data, having the right uncertainty, all these ideas that Jeremy was talking about, it really is bringing mathematical computational techniques into a domain such as social science, which was considered much more qualitative in the past, which I think is very exciting.
Yeah, I mean, companies like Facebook and Amazon and so forth are leading in computational social science in many ways, leading and exploiting it. Any other questions? So it's a great time to be a Bayesian statistician. It's a great time to be an applied mathematician with a Bayesian statistician as a buddy. Yes?
I'll try and compare my horrific questions that I asked Philip the last time when he was doing his sort of line searching of things using just numerics. So if we're interested in computing, I mean, paraphrase a bit what Neil just said. If we're interested in computing complicated things that require lots of data and things like that, there's a lot of computational time, maybe on big clusters and things like that. Is there a model? Do we consider it a bit like signal processing, where there might be a bound at which point, like the rate at which you're reducing your uncertainty and the rate at which you're spending dollars?
Oh yeah.
Times where it's like, should we be? Are certain problems? Is there a boundary that we can't penetrate?
Yeah, absolutely. So Tim and I were talking about some collaborators who work on turbulent combustion. And the reason they're working in turbulent combustion are for the next generation of propulsion devices that don't have any moving parts and so forth. And the thing with mathematical models of turbulent combustion is, one, that you've got differential equations describing all of the chemical reactions in the combustibles, and then you have these diffusion equations describing the formation of the flames and so forth, and these are all coupled. And they're coupled in such a way that the sort of length scales for both chemical reactions and the formation of the flames are round about the same, which means that the amount of computation that's required to capture these it goes beyond what is feasible. And so they know that they're making gross errors. And what they want to be able to do is say, well, I know I'm making this gross error, and I can reflect that in this posterior distribution. The posterior is so wide I can't see anything. So this is a fruitless exercise. But at the moment, all they can say is, yeah, we're making a big error, and it's bounded by this. And so I can run these simulations on the cluster, until it gets to this, but this is meaningless. Whereas if they had this posterior, then they could say, well, the variance is now at such a level, we could do something rational with this distribution. Yes? You need to speak up. I'm old, and I don't have my hearing aid.
The norms that you use to define the modes in the function space when you have the error estimated as forward propagation. What are the norms that you use to define the modes and get the big O notation? Is this with respect to some integral square norm, or how do you do it?
What was it? This was the Sobolev norms.
The kernel norm. So
it's like an integral against the kernel.
Yes. Which is assumed norm
It's like
equivalent.
a mean square error, the weighted mean square error.
Yeah.
And it's also in the setup, it's assumed to be norm equivalent to the Sobolev space of order beta. So the beta that you saw in the convergence theorem is a Sobolev order of smoothness.
Okay.
And of course the equivalence constants in that norm equivalents are being swept into the big O in the convergence rate.
Yeah, in the integration slides, it shows you that it's Sobolev norms that we were using, which I skimmed past.
I think you mentioned epistemic uncertainty at some point in the presentation. Do you also distinguish between aleatory sources?
No, well, I mean, I think that's the question that this chap here mentioned. Is, you know, what are the things that we don't know? And what I'm talking about is what don't I know about the things that I've been given, rather than the unknown unknowns, as it were. So I'm not making that distinction here.
I never liked the distinction.
Yeah, Ian will talk about that.
People have heard me rant about it.
Yeah.
If you try and think in detail what they actually mean, what is random? Really, random is just a set of familiar situations where we don't know something. Okay, and the other classification is things we don't know. So really, the Bayesian view just has everything we just don't know. And you can put one thing in one box and one thing in another, but we just don't know them both. So a dice is random because I don't know it. A coin is random. Weather is random just because I don't know. There's nothing different. And the only time I've been pushed off that argument is when we start talking quantum mechanics.
There's a very nice example of a paper that Percy Diaconis wrote, where they actually ended up making a machine where you could toss a coin. Toss a coin. It's time for my bed, and it would come up heads or tails every time. Run it for a year and you just get nothing. But why? Because the initial conditions were so carefully controlled and they knew exactly. So that's a really nice example of the Bayesian formalism basically describing what we don't know.
I agree totally with Ian, and I think it's totally a statistician separation. That it didn't make any sense to Laplace, that type of separation, and that's why it's embedded in his quote. The probability is for dealing with ignorance, and that's all, because quantum doesn't exist for him. It's just in chaotic systems, you only need a little bit of ignorance, and then it becomes totally uncertain, and that's it. You know, but for other systems, you need a lot of ignorance to. And I think it's an artificial distinction that came in with Fisher and these other people for good reasons, contextual to the time.
So
yes.
Can students start kind of bracketing their incorrect answers on their exams to kind of be like, I reckon I've got the answer within 2 centimeters?
Well, if I ever mark an exam paper again, someone had the sense to do that, I'd give them extra marks, even if the answer was wrong.
If the right answer is within their interval.
Yeah.
So my students have done +1 ±
a lot. That's huge. It's a complex domain too.
Yeah. Great. Well.
Good.
So I'm just quite interested in your social stats idea, because we do a bit of social stats. So your problem over here was allocation of police officers, was it?
Yeah.
And so what you were doing is simulating. You were solving these equations into the future.
Yes. Yes.
Okay.
So yeah.
And did they listen to you? Did they?
No, they didn't listen to me, but they listened to the people that did this before me. And the people that did this before me from University of Los Angeles are now making a fortune and selling software.
I thought in Los Angeles they just put police in rich people places.
Yeah, well, that may well be what the software system's telling them to do.
The inference is different. That's the decision later, right? Yeah.
So in fact, this is part of a project, as I said, with the Metropolitan Police and West Midlands Police and Police Scotland, and they're still talking to me, so that's a good sign.
Kind of a little bit like what Peter Deal was doing, wasn't it, with epidemics? You know?
Yeah.
I mean the old stuff with the NHS number. Or
I don't quite know how he's doing it, but he's still pursuing that kind of thing. So
he's restarted that. So where people keep taking calls from people with gastroenteritis.
Yes, all of that stuff, and they wanted to know if it was epidemic.
Yeah, and it's looking for the probability that it's a
Yeah. So those spatiotemporal models that Peter uses for medical statistics and public health could be, pretty much used as is in this particular scenario here. Why? Well, you're getting phone calls reporting a particular type of crime. It's in a particular area. There are agents, i.e., criminals, that are perpetuating that, and they are moving about, and they're attracted to areas where there is, the underlying epidemic model is, is very much in this particular scenario here. And in fact, one of my students is looking at those sorts of spatial models to do exactly that. So ignoring all of this and looking at these spatial temporal GP type models.
Because Ketelet, who did the earliest social statistics, was inspired by statistical mechanics to take those models into society. And then there's this